Next chapter is simple linear regression, which was covered in the second stat class 2120. Now we're going to look at the linear regression for the purpose of forecasting. So the last few chapters, chapters 2, 3, and 4, we looked at only the sales data as a time series, and we examined, we analyzed the trend and seasonality and so on, and used that analysis for the purpose of forecasting. But now we're going to bring in another variable into the mix. So we have sales, and we're going to try to forecast sales based on another variable, a predictor variable. So dependent variable is y, which is what we want to forecast, and in simple regression, in regression analysis in general, y is called the dependent variable, and it can also, some people also refer to it as response variable. So dependent variable, response variable, they're all one and the same thing, and that is the variable that is being predicted, or in our case it is the variable that we are trying to find a forecast for, which will be like sales. Now x is called the independent variable in regression, and that is the variable with which we want to try to forecast y. So it is also called the predictor variable or explaining variable, predicting variable or explaining variable, and in simple regression lingo it is called independent variable. Now simple linear regression involves two variables, x and y, and we come up with a straight line relationship between x and y. So we will express y as equal to a y-intercept, we use b sub 0 as the notation, plus slope b sub 1 times x. So you have y-intercept plus slope times x. So that would be a straight line equation. And we have a regression model. We will discuss regression model in a little bit, the expected value of y and so on. So these will be when we bring in statistical analysis into the picture. So we will discuss these two concepts in a little bit. So right now all we are interested in is y, expressing y as a straight line equation involving x. And for this we will collect data between y and x, okay, and that would be a time series. So we, for example, if you want to predict number of mortgage applications based on interest rate, so we have interest rate and mortgage applications weekly basis or monthly basis for the past n number of periods. So we'll have x and y for the past as the time series, okay. Or if it is price that we charge versus the demand. So again we have price and demand from a time series, and we have x the price, y the demand. So we have a data set, a time series data set. Now we try to find a relationship between x and y that is a straight line relationship. So how do we develop a framework to come up with an equation? Okay. Now that is called, the fitting a regression line is called ordinary least squares. We're going to be using what is called an ordinary least squares method. So for example, suppose if you plot the x and y in this way, since this is a statistical problem, or there is no perfect relationship between the two variables, okay, it has an influence, x has an influence on y, but it is not a causal relationship. A causal relationship is one where there will be a perfect relation. So if there is a causal relationship between temperature and say length of a wire, okay, maybe there is a perfect relationship there, and you can express that as an equation, and all the points will line up on that straight line. But in regression analysis, we do not have causal relationship. There is an associative relationship. There is a causal component, okay, but that's not all. There are some random fluctuations also involved. So the lines will not line up exactly on a straight line. There will be some deviations, and so our problem is to try to come up with an equation of a line that in some sense is closest to all the points. So we're going to define something like this: a regression relationship that is y, okay, is b sub 0 plus b sub 1 x, okay, for the ith observation. Okay. Now if everything lines up on a straight line, there will not be any random error at all. But since they do not line up, so we have to add a random error. So our estimated y is just this part. The straight line is the estimate. When you add an error, that is the actual relationship. So y minus y hat then, okay, y minus y hat is your error. So here, if you take this part is y hat, so y minus y hat is your error. Okay, so which means the straight line is your y hat. Okay, these points are your y. So y minus y hat. Okay, y minus y hat. Some are positive errors, some are negative errors. Okay, this is the vertical distance between each point and the straight line. Okay, now if we take that error and square it and add up the squared error from all the points. Okay, so that is, you take y minus y hat, that's your error, square it and add them all up. So that is called sum of squares due to error. Now our problem in ordinary least squares is to find b sub 0 and b sub 1, which means find the estimated line that will have the minimum possible value for SSE. And we can derive this using calculus. Okay, so this is how you state the least squares problem. So the objective of least squares method is to determine the values for b sub 0 and b sub 1 such that SSE is minimized. Now that is given by these two equations, b sub 1 and b sub 0. So if you follow this formula for b sub 1 and this formula for b sub 0, then what you get would be a line that minimizes SSE. Okay, so here are some notations your textbook uses. Now, S sub xx, if you define that as sum of squares of x, which is x minus x bar squared sum of that. Now, S sub xy is the cross product of x minus x bar times y minus y bar and sum of that. Then the ratio between S sub xy and S sub xx will give you b sub 1, which can then be simplified to this formula. This is an easier formula to apply, as we will see. And then b sub 0. And there are some Excel functions we can use. So slope is this and intercept is this.